Right, let's start. Okay, today there aren't many announcements. I will just remind you that we have enabled Piazza. So this is now the way we are going to communicate between each other. We have therefore disabled discussions in Canvas because we don't want you to cross-post between the two platforms. So you need us for something, this is the place to go, be it to reach us directly or to share a public post. Besides that, as every time, I will read one of the policies. This one is about plagiarism and cheating, which we have already talked about when we went over the syllabus. So basically, I want to read it out loud because we did talk about it, but it does says, it kind of reminds you of the academic misconduct policy in the School of Computing and University of Utah. So if you have any concerns and questions about that, there are more materials you can see here, including a code of student rights and responsibilities. Okay. Now, there have been plenty of questions about project proposal, which is due very soon on January 25, which is 2 days from now. If you haven't seen this yet, you should really look at it today, because you do need to submit information about who is in your group, what data you plan to use, and where will you get this data, what structures you want to mine from the data, why this problem is interesting, and what is new, or what I, the instructor, will learn. So this last point highlights that this is not just another homework. It's not like taking what we have learned in the class and just applying it to new, like whatever data set you have found. It will be similar in maybe spirit. You will use techniques we have, or will cover in the class, but there has to be a reasoning for why this technique is appropriate for the problem. And of course, there were questions from you about how could you know, like, what can you use if we haven't talked about these things yet? And I understand that, but again, we have a lot of available materials. So first thing you can do is, first you should find a problem that's interesting to you regardless of this course and find some data for it. And we have linked many of those resources where you can get inspiration for both the problem and the data you might want to work with. And then what I recommend you to do is just think of on your own, like what kind of, data this is. Is it a text? Is it an image? Is it like a bunch of demographic features? What kind of data are you thinking about? And then you can go over the course material in the calendar and check the notes for the lectures we didn't cover. Usually the first paragraph kind of describes what is the point of this sequence of lectures. So for example, here we have started to look into the problem of finding similar items, and that kind of was motivated in one of these notes. So what you can do, you and your teammates can divide and cover some of these notes and see, okay, I have a sense that this technique could be, useful for our problem. And you can also look at what kind of inputs the corresponding algorithm is taking. You don't need to understand all the details. You just need to have a good sense that you think that this might be applicable to the problem you are looking at. And then again, data mining is a hot topic these days. So there is a lot of resources on the internet. Usually if you search, you will find a lot of ideas. If you have, you want to apply graphs to a problem and you didn't see anyone applying graphs to that exact problem, that can either mean, okay, you find something super interesting, or maybe maybe you are trying something that is not really a good idea. So kind of two extremes. And you can also ask us whether we think that's actually a good idea. So to kind of summarize, what I suggest is look through these notes, divide the workload. Don't let one person look at everything. Try to get a sense of what would make sense. And then when you write your proposal, if it turns out that you had, try to apply something, some algorithm to the data we think is not, if we think that's not a good use case for it, we will tell you, and you will not lose the points for it. So the purpose of this proposal is also for us to give you feedback on whether your project makes sense. So as long as you submit what is written here, you should be fine. And if we think you need to pivot your project, we will let you know. Second question that was frequently asked is about whether you can use data and tasks you are working on for your machine learning project. And this is a little bit, yeah, I don't have a like super strict no or yes here. Basically, ideally, what I would like you is to work on completely other problem and on completely other data. The reason being is that finding the data and thinking about this data and finding way to represent this data is the major component of any data mining project. So it is one of the crucial part of the project you are going to be working on. Now, if you already had, prepared data from before, that kind of, that part is getting lost. That said, I can understand if you are very passionate about certain problem, or if you're a PhD student and you want to kind of do a little, digression from your research, but still work on the same problem, just, use completely different techniques. It should be fine. You will still need to justify that what you are, submitting for your machine learning project is notably different from what you're going to do in the data mining project. And of course, there is a question, what is notably different? So for me here, notably different would be that you are using very different technique. So for example, if you are using, and you will use classification in machine learning project, then it might make sense, to apply clustering technique in your data mining project, because classification and clustering are very conceptually similar. Them being conceptually similar doesn't mean that clustering is a good approach for the problem. And you need to kind of justify that this other technique you're going to use in the data mining project really makes sense for the problem you are looking at. And ideally, that other technique would require you to represent your data differently, and therefore your pre-processing of data will be different as well. So if we do see, you are working on the same problem, but you can justify, well, why are you now using this data mining approach in this project? And there is sufficient differences in our opinion, you should be fine. But I can't tell you like right now, how exactly are we going to quantify it, because it's such a weird thing to try to quantify. So ideally, you just wouldn't submit to, you wouldn't work on the same problem. If you still have doubts, reach out to me directly, and I can let you know what I think. We will check whether the projects are too similar to those submitted in machine learning. That's going to be very easy for us. So yeah, any questions about this? Yeah.
If you couldn't collect the data that we already proposed in the proposal, can we change it?
So just a clarification question is, are you talking about data that you, for example, wanted to scrape, or the data that you are hoping to find? Hoping to find. Okay, yeah, that's fine. I think you can specify that you are looking for data of certain properties that are needed for your problem. If you do not find the data, then you are in a little bit of trouble, because then you need to also change the underlying problem that you're working on. But that's fine. Just try to figure it on time, because the next project component is going to be due on February 15th. So yeah, try to figure it out on time whether you do have the data for the problem. And if it turns out that you actually can't find it anywhere, and you can't scrape it from anywhere, it's pivoting is totally fine. Yeah. Yeah. Any other questions about projects? Oh.
Is it alright if a project proposal goes above 200 words? How long should the project be going to be? How long enough to complete?
It should be 100 to 200 words. So this much.
Right.
Yeah, and less is always better. If you can be as concise as possible, we would appreciate it because that means less reading for us. More than 200 words. If you really can't fit it in 200 words, yes, sure, a little bit longer is fine, but not much longer. So try to be close to 200 words. Mhm.
Also, the project proposal is not the place where you're going to detail that you plan to use this technique and this and this.
No, so basically here, let's go over this stuff. Okay, which data do you plan to use? All right, you say I will work, but I don't know, this kind of problem. I am looking for data for that problem right now, or you already found the data set and you will just say, okay, I will use this data set. What structure are you going to mine from this data? You will say, okay, I'm working with text. I will represent this with, let's say, sets. And then you don't need to specify anything else about the actual algorithmic approach you are going to use it here. You can mention it if you want, like I'm thinking about these techniques. And then you will tell us why working on this is interesting and what might we learn from the way you go about this. So you do need to like specify a little bit because it's going to be hard to answer these two questions if you don't say anything about how you plan to go about this, but you do not provide any details yet. Yeah. There will be other components of the project for that. Okay, I think that's all. Again, we have office hours after the lectures. So if you have any other questions, if you want to run something by us, come there and we'll talk about it there. Okay, I will turn these things off. Okay. All right, let's start with the lecture then. Just a moment. So just to remind you, what are we doing here? This is like a second part of our 3-lecture series on finding similar items. So our goal is given huge collection of instances, for example, huge collection of documents. We want to find most similar instances, most similar documents, and we want to do it fast. We don't want to take this to take, a week or a year. So that's our main problem, if you remember. And then we said, okay, we are going to do this in 3 steps. Last time we have converted documents into sets of k-grams. So for example, sequences of 2 words. And then we have measured similarity between the 2 documents by computing Jacquard similarity between them, which is the ratio between their intersection and union. Okay, so this is what we have done last time. And we said, okay, today we are going to focus on a problem where our sets that represent our documents become large. So we have too many, let's say, k-grams if we are working with characters, which can totally happen if our documents are long, which is a completely realistic situation to be in. So what are we going to do today? So I will just write it down for the record. Problem we have right now is that we have large sets of k-grams. And what we are going to do today is we are going to try to convert these large sets into small vectors, which we are going to call signatures. But we want to convert them into signatures such that we can estimate Jacquard similarity from these signatures of these sets. So here we have a vector representation of our set. And when we compute the estimate of Jacquard similarity between 2 signatures, we get approximately Jacquard similarity between their sets. So we need to have this property. We can't represent, or at least we are not trying to represent them with any vectors. These vectors, these signatures we are going to construct today will have this specific property. Okay, and this is all we are going to do today. Then on Wednesday, we are going to utilize this thing for LSH, which is the solution, the final solution to our problem of finding similar documents in a large collection of documents. Okay, so this lecture today will look like a sequence of things we need to construct to actually get to these signatures. So first thing we are going to construct is something that's called characteristic matrix. And what this is a matrix where in columns you will have your, these columns will represent your sets. Let's say we have n of them. And in your rows, you will have the elements from the universal set from which we are constructing our sets. Okay, so elements of S1 to Sn are these some of the items AI to AM. And in this matrix, we will have values 1 and 0. And 1 will be in particular when an element is actually in this set. Okay, so that's it. So we will have some zeros and 1 inside it. And this is not how we actually store the data because it's too sparse. We will have too many zeros. So it's going to be more efficient for us to actually remember locations in this matrix where we have ones. So this is not how we are going to in practice actually construct our representation of data, but it's a very useful way to visualize data stuff. So when you think about this problem conceptually, you can map something like this in your head, but you will not actually implement something like this. Okay, I will quickly write this down. Okay, so let's look at an example of how we could construct this matrix. So let's say we have S1 equals to AD, S2 equals to C, and S3 equals to BDE, and S4 equals to ACD. All right, so we have 4 columns, right? And we can take our universal set to be all the elements that occur in this documents. So we will have A, B, C. Let me just do something. Alrighty, we'll have A, B, C, D, E. But we will actually represent these elements with integers, just like we did it in the first real lecture we had. So we'll have 0, 1, 2, 3, 4. Okay. And then we'll have here 1 because A is in S1. Then we'll have 0, 0. Then again 1 because D is element of S1. Then 0. Then we'll have here 0, 0, 1. 1 because C is element of S2. 2 other zeros. 0, 1 because B is element of S3. 0, 1, 1. And then for S4, we'll have 1, 0, 1, 1, 0. Okay, so this is one way to represent our data. And right now I'm working with matrices. I want to represent all of these 4 sets together, but you can also kind of remember from this that now each set is represented by vector, right? Each column is a vector representation of corresponding set. Okay, and in the problem with documents, what we have here in rows would be our k-grams. So what we call here A, B, C, D, E, and so on. This would be those k-grams we have collected from our corpus. And if a document had a k-gram, we will put 1 for in the corresponding row and 0 otherwise. So I try to kind of connect this with the problem we have talked about last time. All right, now we are going to introduce min hash value. And again, this will not be a way we are going to compute min hash values in practice, and we will come to how we will actually implement this. But this is, again, a nice way to kind of conceptualize this. We start with this ideal thing, and then we will try to make it more efficient in the implementation. So we need to go over this, but this is not actually what we are going to implement. So I will write here concept, not implementation. And sure, some of you are wondering, why are we talking about this thing right now? Again, we are in the process of constructing that signature vector, which will be a smaller vector representation of that large set. So we are just putting things in place here, and in the end, they will connect to this thing, which will give us this signature. So bear with me for a moment. Okay, so the first thing we are going to do here is going to permute the rows of our characteristic matrix. Okay. And then we are going to define min hash value of column, okay, of this set, let's say SH. It's going to be actually the min hash value of its corresponding column in the characteristic matrix. And it's going to be the number of the row where we encounter first one. So if you look here, for example, for S1, our first one was here, and the corresponding row number is 0. So its min hash value would be 0 if we took the permutation of the rows that are exactly in the original order. Okay, so mathematically, we can write this down as taking argmin from, not argmin, just min from all the rows we have, which are from 1 to m. Okay. We'll take all the k's, we'll take a permutation of the column where SH is, and then take the k version of it. Okay, so this is just another way of writing what's written there in words. Okay, so what I would like us to do right now is try to practice this again using that poll. Okay, for that I need to get out of here. Okay, we'll have 3 polls today. All right, so what I want you to do is do the following. We'll have these 4 sets. You will represent them first by changing the letters A, B, C, D, E to the actual integers 0, 1, 2, 3, 4. Then you're going to pick the order of rows B, E, A, D, C for your characteristic matrix, which is the first thing we need to do when we are computing the min hash value. And then you're going to compute and report the min hash value of sets, all of these sets in the order that I ask. So let's make up some numbers. Let's say we had min hash values to be 1, 2, 3, 4. For S1, S2, S3, S4, you will just report sequence of numbers 1, 2, 3, 4. That's what you're going to put here. Okay. Would it be useful to open the slide as well, where we define the min hash value? Okay. So that's the question. Okay. All right. So just a reminder how we are calculating min hash value. We need to permute the rows in some order. Usually we do this randomly, but in the question, I have given you a specific way to permute the rows. So do that permutation of the rows. And then you need to calculate for each column the number of the row where we find the first one. And count the rows from 0 to 0, 1, 2, not from 1. Okay, do we think we can do this, or is it too complicated? That's a good question. Okay, so here we have a characteristic matrix, right? And the order is in the original order, A, B, C, D, E. When we say permute the rows, this means you just take these rows and switch their order. Yeah, and the specific order I'm asking is B, E, A, D, C. So, all right, what I think it will be useful right now is to keep this specific slide open, write down the permutations of the rows, specific ones. So this one, okay, no. All right. So the first thing to do here is look at this matrix and change its rows in this order, which is B, E, A, D, C. Okay, this permutation, B, E, A, D, C, maybe write this down so it will be easier. Write the permutation down. Okay, and now permute the rows, and then when you are done, let me know and I will tell you what the next step is.
Permute the rows or all?
Permute the rows. Just do it. Don't think too much about it. It's a instruction. Sorry, second. Okay. Yes. Okay. Raise of hands for everyone who knows what they are doing right now. Okay. Permuting the rows. Okay. Okay. I sense this might be a little bit confusing. So let me write this down. So we have permutation is B, E, A, D, C, right? So now we are going to have rows B, E, A, D, C, 0, 1, 2, 3, 4. Okay. That's one. All right, so let me use some colors here. Maybe, all right, so let's find where the row B is in the original matrix. This is row B. So now we are going to put the values of row B as our first row. We changed what is the first row. Now B is the first one. So we have 0, 0, 1, 0. Then we look at the second one we need to put here. It's E. We are going to put row E in the second order. So we have 0, 0, 1, 0. Then the next one we need to put is A. So that's our first row. We're going to put 1, 0, 0, 1. Then we have row D, which is this one here. We'll have 1, 0, 1, 1. And finally C, 0, 1, 0, 0, 1. Okay, so this is permutation of rows. We just switch their order in the matrix. That's all we do. And as I said, when we do Minhash, when we calculate actual Minhash values, we would find this permutation randomly. That's important. But here I had just given you one. Okay, so this is now permuted matrix. That's our first step in calculating Minhash value. Now the second step is that for each one of these sets, we find where is the first one in the corresponding column and report the row where we found it. So here we would have just a moment. Okay, so here we had for S1, let's calculate. Okay, so this is going to be confusing. Actually, no. All right, so here we have our first one is here, which is row 2. Okay. And then for H Minhash S2, we have 4, and so on. Is 0. Okay, so excuse me, I didn't see that this is overlapping, but that's it. So we had, these are the hash values, Minhash values that we have found for these sets. Go ahead.
So when we commute the rows, we change the letters assigned to the rows, but we and the obviously the characteristic matrix part, but we keep the indices of the rows. So the 0, 1, 2, 3, 4 on the left side that stays in that order.
Yes, I think so. But now I'm overthinking it and I am not 100% sure. Yeah, it should be the number of the first row where we find the corresponding value. Okay. Let me just double check that. I'm kind of afraid that I don't tell you the wrong information here. Actually, that's not correct. Apologies. I switched this up. So it should be A 0, B 1. Okay. All right. Okay. Let me just find my cursor. Okay. Three, 4. Okay, so it's not the row, it is the actual element in the permuted order. Thank you. Like I completely switched these things up. So for S1 it will be 0, and then for S2 it's going to be 2, for S3 is going to be 1, and for S4 it's going to be 0. All right, so that's Minhash value. I hope it is clear how to go about finding it. And you might wondering now what is so special about Minhash value.
Can you go back to the value?
Yeah. Yep.
What if the value is same no matter what you get, like what if no matter what order you do with it, if you're keeping the same numbers, like because if you didn't move that around, you still have the same answer, 0, 2, 1, 0.
The answer shouldn't be the same, right?
Because if D was the top row, then it would be 3 first. Right?
Yeah.
Because we're reassigning, we're keeping the numbers with
Yeah.
the letters.
Yeah, basically this row has, we have permutation B, B, A, B, C, then here we would have 3 as our hash value for S1.
Is there only one hash value that represents these values together?
What do you mean by together?
Like a string, for example, that would reflect all of these 4 results together.
We are going to put them into a vector and represent them together. Actually, we won't do that. We will use different hash functions. I mean, maybe, I don't know, but that's not what we want to do. Is there a specific situation you're thinking of right now where you want to do that?
Hash value in security or
I don't know about security that much to make a connection there. Right now, we are just going to make a min hash value for every of these sets separately. And then later on, we are going to do something with them. But for us right now, combining them in some way is not important. Yeah, for this specific use case of finding similar items. All right. Good. Okay, so let's go further. So what's I said, what's special about this min hash value? And an interesting property that min hash value has is that probability of min hash value for S1 being equal to min hash of S2 is actually Jacquard similarity between S1 and S2. And remember when I said in the beginning of this lecture, we want to represent these large sets with these signatures, but these signatures have to have certain property related to Jacquard similarity. The estimated similarity from the signatures have to be equal to the actual Jacquard similarity of the sets. And this is where kind of that property is emerging. Okay, so to see that this probability equals to the Jacquard similarity, we are going to focus on the columns that correspond to, in the characteristic matrix that correspond to these two sets. So C S1 and S2. And we can divide rows R into 3 categories. We'll have type X rows, where R S1 and the value in S2 for that given row R are both 1. Then we have type Y, and there CRS1 can be, for example, 1. And the CRS2 is 0. Another way around, CRS1 equals to 0, and CRS2 equals to 1. And then we have type zeros, that where CRS1 equals to CRS2, and they are both 0. Okay, so situations where the element in that row is both in S1 and S2, situation where it is in one and it's not in the other, and the third situation when it's not in either of these. And then we can define X as count of type X rows. And since those are all the elements where this element is both in S1 and S2, then that's equal to the cardinality of their intersection. Then we can count I rows, type I rows. And these are elements that are either in one or the other element, but excuse me, either in one set, but not the other. And those are, as we know, elements of symmetric difference. So we have as many I rows as there are elements in the symmetric difference of these two sets. Okay, so now we are wondering about the probability of mean hash S1 equals to mean hash S2. That's our thing here. And to answer that, we are going to look at the probability that first row we are encountering is X row. So the row where the corresponding element is in both of these sets. And we are just going to use the standard probability of outcomes. So there are X such rows because we defined with small x, excuse me, this should be large X, large I, and large Z. And small x is the count of type X rows. So there is X such rows divided by all the interesting rows for this calculation. So here there are X plus I of those. We can ignore zeros for this calculation. They are all zeros, and there are too many of them, so they are not important. They are 1 over Z, where Z is huge, is close to 0. So these are not important to us. Okay. And then we have, we can look also if the first row is, excuse me, something else I wanted to say about this is that, actually, let me go over this. What if the first row is Y type of row? What do we know about mean hash values then? Well, if I rows are those where we have 1 in one column and 0 in the other. So we know that mean hash values of these two things will be different, because if you had already encountered 1 in a row of a certain column, that's going to be mean hash value of that column, but we haven't encountered 1 yet in the other column. Therefore, this element will not be the mean hash value of that column. Therefore, these two things are going to be different. So just try to visualize what mean hash value is. It's the first time we encounter 1 in our column. If we had encountered 1 in one of the columns, but not in the others, then that directly implies that their mean hash values will be different, right? I expect more nodding on this point.
Can you go back to this?
Mhm. Yeah. Is there anything specific to clarify here?
Yeah, can you just explain it again? Like you're taking each row and you're comparing it with the set that you've seen so far?
Yeah, so C here, C is denoting the corresponding column of a set. So here, this thing is telling us this is the first column, excuse me, this is the column of the set S1, and the other one is the column of S2. Now we are looking at, if we look at the rows of those two columns, what kind of situations we might encounter. We might encounter a situation where we see in the same row of those columns 2 1s. That's one situation. Then the second situation is that we can encounter 1 in one column, but 0 in the other. And the third situation is there are 2 zeros here. Now we are kind of making our progress to showing that the probability of mean hash values of S1 and S2 being equals to their Jacquard similarity. And we didn't come to that point. We are kind of deriving the things we need. One thing is that we need how many type X rows we have, how many type I rows we have. These are the two things we have calculated, okay? Now we are moving on to certain situations which will kind of lead us to the conclusion that this probability equals Jacquard similarity, but we are not there yet.
Thank you.
You got it. Okay, so we have seen that if the probability of seeing in the first rows of these two columns is X row. So we kind of make our progress towards this column, and the first thing we have encountered is 2 ones. We can find X over X plus Y such situations, basically. So that's our probability. Now we are looking at the probability that the first row we have looked at is I type of row, where we see 1, 1 and 1, 0. And I'm saying here that in this situation, we know that mean hash value of S1 will definitely be different from mean hash of S2. It's impossible for them to be equal here. Yeah. So together, when we look at the mean hash of S1, and again, here we can safely ignore zeros, then these two things being together is actually equals to the probability that the first row equals to X row. Because if the first row is not X row, it's an I row, we know that the mean hash will be different. So the only possibility of these two things being together is when we have X rows. And we have actually calculated what that is, and that it's equal to X over X plus Y. And that we have seen equals to the intersection over intersection, cardinality of intersection, plus the cardinality of symmetric union. So this is X, this is I. And therefore we know that this equals to intersection over union, which is exactly our Jacquard similarity. Okay, and that's it. We have now seen that the probability of two mean hash values of two sets being equals to the Jacquard similarity of them. And this is just a probability. And I hope what you have kind of figured out in the first homework we have is that you can be very lucky or very unlucky. And in the first trial, you can get something that's not really reflective of this probability, right? So we like to talk about expectations, like in this first homework we did. So we want a better estimate of this. And how to do a better estimate than to repeat something multiple times, which for this specific problem means that we are not going to use one permutation of our rows. We are going to use many of the permutation of the rows, right? So we will have multiple associated hash values.
So is it ever reasonable to use all permutations?
It is not reasonable if you really want to implement this, right? And that's what we are going to get to next, that we are actually not going to use these permutations of the rows.
Oh, so when I lose an example.
This is, I don't know, have you been here when I said this is a conceptual framework? Yeah,
This is not.
Yeah, this is not the actual implementation, but it's going to be important to go over this to actually understand why are we doing the implementation we are doing. Basically, kind of a spoiler is we are going to use another hash function that simulates the permutation of the rows. We are not actually doing it, but this hash function will kind of simulate where your element would end up if you permute it. Yeah. All right, so better estimate, repeat as always. And here that means multiple permutations. Okay. So we are going to use K permutations. And which means that we will have a K mean hash functions. So that mean hash value, I was saying that's a hash function that gives you this value, right? And it depends on the permutation you have done. Depending on different permutation, you would get a different mean hash value. So that's what we are doing here. We are taking K different permutations of our rows, and from them we are defining K different hash functions. And when we talk about hash functions, we had said the choice, the permutation here is random, but then the hash function itself is deterministic, right? Once we fix the permutation, we always get the same value for our set. Okay, so these are K Minhash functions determined by these permutations. All right, and what we are going to do is what's called signature matrix, where we are going to have values of each one of these hash functions for a given set put into a column. So here we will have H1 S1 up to HK S1. And we'll do that for every one of our sets, which we have, I believe, excuse me, this is wrong. We have n of them, and that's it. Okay. So this is called signature matrix. Okay, so this is an important thing for us, and this is going to kind of be close to what we want. Here, if we chose K, that's kind of smaller than our number of elements M, let's say 2, we would already get this kind of little vector representation that we wanted. Again, this is not actually what we are going to do, but it's again useful for just to think about these things conceptually. So you can basically think about each one of these HIs, the vector you get it, each one of these rows as an independent experiment. And then when we do some averaging, we will get something which in estimate gives us the Jacquard similarity. And to write all of this down, we will define a variable, random variable XL, which is 1 when the Minhash value. I will use M for Minhash just so I have less writing here, between any kinds of sets to be 1 if their hash values equal to 1. Okay, and 0 otherwise. Then we are going to define an average of these things. Okay, and let's now look at what's going to happen with the expectation of the average of the variable like that. So we are going to just put what x hat is, which is 1 over k, sum L from 1 to k xl, because the expectation has nice properties. We can do the following. And now we know that expectation of a random variable equals to the value times the probability of that value. Okay, and we know that here the only things that are going to survive are those elements where we have the same hash value, and the probability of such kind of outcomes is given by Jacquard similarity because we have just calculated that. So here, maybe it's not clear. This will be, now I'm running out of space. This thing here, when XL equals to 1, then this probability is probability of HML. So Minhash value L being equal, and we know that this value, because we have just calculated it, is equal to the Jacquard similarity of these things. Okay, so when we put Jacquard similarity here, and when we sum it k times, we will get k times Jacquard similarity but we have this normalizer here, 1 over k. So in the end, we will get just Jacquard similarity of S1, S2. Okay. So this is why we introduce this k Minhash values, which are all corresponding to the k different permutations. Because when we take their expectation, when we do this thing k times, we will get better estimate of Jacquard similarity than if we have done this only once. That's the point of introducing the k of them.
Can you explain again, like the XE and what that means in words?
Oh, okay. This is called an indicator function, which is a way to write this. So this is equal to 1 when HML equals SI equals to HML SI and 0 otherwise. So when 2 Minhash values of sets SI and SI are the same, this random variable will give you 1 and 0 otherwise. That's how we can write this down. It's just a math notation for the same thing.
And then the X hat, that's
The average of these random variables. So that's a new random variable that you define by taking the average of these random variables here.
so how many times within that matrix there's a 1?
Yes, but since this is a random process, it's better to talk about it in, like including some randomness here.
And what's the L?
L is just a way to, go over the summation. So this is the same as S, 1 over K, S1 to SK. So we just use L to go over the summation. Yeah. Okay, so we have finally come to something that looks like signatures, but as I keep saying, this is not the actual thing we are going to compute. So how we actually computed it follows. So computing Minhash signatures in practice, or it's implied. So the problem with doing something like this, constructing this matrix, is that each one of these Minhash functions we have defined require us to permute those rows. And we have seen an example of very small matrix with only 5 rows. But remember, the rows correspond to elements of our universal set, and there will be a lot of them. So when you need to permute a lot of such rows, that's going to be a costly operation. It's not going to be cheap to do that. You will actually also need to store all of these k different matrices that correspond to k different permutation of these matrices.
Are the features going to be sparse or?
They're going to be very sparse.
So using a matrix in general, are there so many matrices or?
No, as I said, we will not, because I said this is just a visualization. It's not the way we started.
The matrix is like, so how is it stored?
Yeah, so we are going to now go over the algorithm, how to compute these things, and we actually won't store anything. So we're just going to make the pass over the elements of the set, and we are going to do some basically check whether something has happened. And if it has happened, we are going to do something with a vector that has as many elements as we have this Minhash. Yeah. That's correct. All right, so the problem with what we have seen so far is, so just to kind of, the problem is making these permutations and storing large matrices, but we do have nice properties of the things we have seen so far. The most important thing being that the estimated estimation of the variables we have defined will be equal to Jacquard similarity. So that's a really nice thing that we have. So we want to have something which is more efficient, but exhibits those kinds of properties. Okay, so we are going to construct. So just to record this problem, large matrices. So we have, multiple of them, as many as we have permutations, plus that is times permuting the rows. And this is going to be slow, which is bane of our existence in this course. Okay, so what we're going to kind of do now is try to simulate permutations, basically. So we are not going to calculate these permutations, but we are going to introduce hash functions, which will, at least conceptually, we want them to have a property that when we hash the row, row value, that we get the position where that element would end up if we had actually permuted it. So there is no guarantee that's really going to happen, but this is kind of the motivation for this approach. All right, so here it goes. We will call it fast Minhash algorithm. First thing we are going to do is we are going to choose k random hash functions. And know that now we have so many introduced, so things can get a little bit confusing, but when we calculated min hash value, we have a specific min hash function for it that is determined by the permutation of the rows. Here, these are not the hash functions we're talking about. These are just any random hash function you want. So we can define them by, let's say, age I goes from some domain, let's say some representation. This, if you remember, these are sets from 0 to m, and let's say these 0 to m's represent some elements in your universe, and you will hash them to against some integers up to n prime. And it's not really important what n prime is, except that it should be large. And I will come to that point when we go over the algorithm, why it should be large. Okay, so let's say, imagine that we are dealing with 3-gram characters. Here we would have as our domain. So this thing would look like, for example, we would have sigma, which represents all letters in English language, A, B, C, so on, and we will put it on 3. So that would be one domain. Okay. In the first actual lecture, when we talked about hash functions, we did introduce some. We had said there is some that are built in Python, there are these and that. So these are the hash functions one could use here, okay? All right, so we have chosen k random hash functions. Then for a given set S, we are going to calculate its min hash value by, first of all, initializing what we call signature. Okay, so excuse me, what I have said here for a set S, we are going to calculate min hash value. We are not calculating that. We are calculating that signature, which is that small vector that represents the actual set. And then what we are going to do is estimate Jacquard similarity from those little vectors. And that's going to be our estimation of Jacquard similarity. So here we are actually calculating signature, and we will call it V. And let's put S here to remind us that this is for the set S. And this vector will have as many elements as there are hash functions. So we are going to have k elements, and we are going to initialize it with infinity. Okay. Is this notation also clear when we have brackets and then subscript and subscript like this? This just means that we are making a sequence of this many elements. Doesn't matter. We can do it like this as well. And we can say there are k of these. Okay. All right, so now the algorithm goes like this for every element that's in this set. And for every possible hash function, so we have k of them, we are going to check is the hash value of that element smaller than the current value of the signature at the same position. So if we took the first hash function, we are going to check is the first element of our signature larger than the hash value. And if it is, we are going to then update that specific value in the signature with the value of the hash function. Okay, and finally, our Minhash or whatever kind of, so we are going to get this signature, and this signature is for us kind of equivalent of the Minhash value. So in the end, we are going to say that Minhash value, one corresponding to one hash function j, excuse me, I, is equals to the same element in the signature. Okay, so this is a little bit, I think, funky to see it like this. What will become clearer when you sit with this is if you think about the values of hash functions for a given element as if that's where this element would end up if you randomly permute the orders of your rows. So like if you are making analogies, here the value of hash functions is the position where a certain element would end if we had actually permuted the rows, which we are not doing.
How should we pick K for this?
Okay, that's an excellent question. I will get to that, but it will take me like 10 minutes to go over it. Yeah. But I will try to get to it. If I don't get to it today, then next time, because I will try to make you solve one of these polls again. Okay, so I was saying that the value of hash functions here is kind of simulation of where the element in the row would end up if we actually have permuted the rows, and the value v is our analogy of Minhash value if we had actually permuted the rows. Okay, and then if you go over this, you will see it kind of makes sense to do it in this way. One important point here is that we just go over our elements of the set once. So we just go one by one. We don't store it. We don't construct this characteristic matrix. We don't actually permute the rows. We're just going over it on fly and calculate the signature, which is great, right? This means that everything is way faster. And I have said here that n should be large. And the reason for this is that if so that nothing prevents us that these hash functions are having collisions, right? So we can hash two of these elements into the same thing. And when we actually permute the rows, they will never end up in the same position. So that's not what we really want. However, if we make the n prime large, then for small initial steps, for small values of k, we won't have as many collisions. This is going to be a rare event because if you have huge n prime, it will take a certain number until we get collisions. So that's why we want n prime to be large.
So what is hj of x again that you're doing like in the last line?
Yeah, so that's a value of a random function for that specific element. And we didn't define them here, but try to remember the first real lecture we had. We have gone over a few options. So here, for example, actually, I will now make you solve something. We can do it together for one. So, okay, so let's take again S1 to be AD, which is the same S1 we had before. And we will turn AD into actual integers. Remember, A, B, C, D, E is 1, 0, 2, 3, 4. All right, and let's choose now two hash functions. So let K be 2, and let's take H1 to be x plus 1 mod 5 modulo 5. And let's take H2 to be 3x plus 1 modulo 5. Okay. Remember, we said that this is not the best choice for hash functions because a lot of times there might be collisions, or for some elements there will never be collisions. It might be prevented when we take, a prime number here. Not the best choice of hash functions, but just for the sake of demonstrations, here are two of them. Then we said, okay, we need to initialize a vector. That's our signature, and there are going to be, the size of this vector will be as many hash functions we have here, which we have 2. So we have 2 elements in signature, and we said we are going to initialize them with infinities. Okay, now our algorithm says go over the elements of your set and then go over the hash functions for that element and check whether the current value of the signature is larger or not. If it is larger, then update the value of the signature. So for first element, which is 0, we would take J to be 1. Okay. Then we'll take first hash function and the value of it for that specific element, which is 0. So 0 plus 1 is 1. 1 modulo 5 is 1. Okay, is this value larger than V1, which is infinity? It's not. Great. Then what we are going to do is update the first value of the signature. So we will have 1 and then infinity. Great. We are moving on to the next hash function, which is J equals 2. And we are going to have the value of H2. So we have 3 times 0, 0, plus 1 is 1, 1 modulo 5 is 1, okay? Is this value smaller than V2, which is currently infinity? It is smaller, okay, we updated. So we'll have V1 to be equal to V2 equal to 1. All right, now we move on. We are going to our next element, which is x equals 3. We again look at J1. J of 1 for value of 3 is 3 plus 1 is 4. 4 modulo 5 is 4. Okay, is this value smaller than the current element, V1? Currently in V1 is what? 1. Okay, it is not. We don't do anything. We go to J equals 2, H2 for 3. We have 3 times 3 is 9, plus 1 is 10. 10 modulo 5 is 0. Is 0 smaller than V2, which is how much? 1. It is. All right, we are going to update our signature in second value. It will have 0. Okay, this is our signature for the set S1. And as I said, each one of these elements now represent what would be a Minhash value when we take a certain permutations of the rows. Okay. What's going to be useful to go all the way to the beginning of the lecture is to compare signatures of two sets. And that's going to be estimate of our Jacquard similarity. Okay, so what I wanted you to do is to calculate the signature for S3, which is BDE. All right. Let's try to do that. Okay. So we have it here and just present it. All right. So try to do this. So the first thing we are going to do is initialize the signature. We are going to use the same two hash functions. So one is going to be hash function number one is going to be x plus 1 modulo 5. And the second one is going to be 3x plus 1 modulo 5. Two hash functions, okay? K equals 2. We initialize the signature with infinity, infinity. And then we do the algorithm. Are you done? What did you get? Okay, since we are running out of time, I will stop here. I hope you are getting something similar to this. Okay, so these are the steps. Just move. All right. So basically, you have three elements. You will go over all three of them, and you are going to check the hash function value for each one of them. And in the end, you would get some 0, 0. And one thing then that's important and didn't say is how would you estimate? I will share this. You'll have all of this. So in the end, how you would estimate Jacquard similarity is to check for how many dimensions in the signatures you get the same value. So here, here we don't get the same value, so you would count 0, but here we get the same value, so you would count 1. And you would do that if you had more dimensions in your signature, you would do that. So in the end, you get that the estimated Jacquard similarity is 1/2. but the actual Jacquard similarity for these two sets is 1/4. So your estimate was not so great. And this goes back to the question of what is the choice of K we would need to take for us to get a good estimate. And there is actually an answer to this, which I would not go into today. I will go over this next time, but we will use something called PAC, which are general bounds we use to kind of answer questions and think about how to aggregate more and more data to get better estimates. Okay, and that's for next time then.
You go back to the last slide.
Yep. Yeah. So I said yeah, so remember last time when we have big runs and then we have a set of big runs, that's basically, so here you have IM and seven, remember? So what we don't have any like you have, you know, no documents, no noise, so that won't happen. Like that's a good question to ask in terms of math, but your documents, your item will have words or whatever else you're working with, so that just. No, that's more like a math term. In a relative set means you have all the words or all keygrams that would be different something. So basically when we are drawing elements to make a set, like a smart here, we are drawing elements from the universal set. So that's all the possibilities, right? Yeah. Yeah, got it. Let me just turn off the Zoom. If I ever find it again. Yeah, you got it.